Hello, thank you for coming to this talk, absolutely after lunch, so I hope you're caffeinated, otherwise you can sleep on the back. So the talk today, as the title explains, is going to be about how we run Flink at Yelp, especially on our Kubernetes setup. And the guy speaking now is a computer guy working on the stream processing team. I'm based in London, but the team is also based in San Francisco. So let's start. For the few of you that probably have never heard about Yelp, Yelp's mission is connecting people with great local businesses. In order to do that, we have a website and an iOS and Android app where people can search for a business, look at reviews, and then connect to the business, make a reservation, request a quote, and all this kind of stuff. In order to provide personalizations for like search result personalization, recommendation, and other stuff, we do a lot of machine learning and real-time processing, and that's where Flink comes to play. But we'll see it in a moment. So what you're going to see in this talk are mainly three things. First one, what Flink at Yelp looks like. Well, I guess that wasn't the title. So basically, we're going to see the main use cases we use Flink for and why we like it so much. Second, we look at how we run Flink on Kubernetes, especially with a closer look at our Flink operator. And lastly, why platform integration matters to us. And with platform, I mean PaaSTA, which is our custom platform as a service. We use this integration with PaaSTA, which is what is used by developers to run REST services, in order to make the platform much more usable for them. So let's start. Flink at Yelp. First of all, Flink is powering our data enrichment and transformation platform as a service. What we give developers is a way, via configuration files, just regular YAML, to write down SQL queries, to manipulate data, or on window joins, and all this kind of stuff. So people can just deploy, actually commit, and push a YAML file, and then we'll automatically generate a Flink job from them and running their job in our clusters. Another big use case that we have is real-time notifications. We are able to send customized pull notification to users that suggest relevant business nearby them. Another big one is user activity sessions. So we are able to create user activity session coming from different platforms. So your mobile phone, and then when you look at the website, also we can connect that in order for downstreams application to the compute analytics over these user activity sessions. One of the biggest applications on Flink that we have, and we're pretty proud of it, honestly, is our connectors ecosystem. So at Yelp, we built a data streams layer, which is called Yelp Data Pipeline, where we run thousands and thousands of Kafka streams that are all schematized with Avro schemas. And we are able to take this data and move it to some specific data source, or even collect it from specific data source and then move it to Kafka, thanks to Flink. What we support at the moment is Elasticsearch, Amazon Redshift, Cassandra, Amazon S3, and MySQL, but many more can come down the line. You just need a Flink application at the end of the day. Now, to get an idea of the scale we operate at, because it's pretty easy to say, yeah, we operate Flink at scale. Yeah, but which scale, right? What scale? So we run only 10 apps, not that many, but we have around 50 clusters, and we have around 1,000 jobs. Actually, we have many more, but since they're automatically generated, it's a bit hard to understand how many we have. So I just played it safe here. Just to get a sense of the crowd, so who's running at a smaller scale at Yelp? Just raise your hands. 42 people. Ooh. Who's running more or less at the same scale of Yelp? No one. Who's running at a bigger scale of Yelp? No one. Who's at the wrong conference? Maybe you thought it was SparkConf, something like that? Okay, sure, whatever. Regardless of your scale, maybe if you're running at a smaller scale, you can get some of ideas of when you may need to consider a different architecture. If you're running at a larger scale, maybe you see a couple of things that you like and you can introduce in your architecture, or maybe you can just come to me and say, hey, you're doing this wrong. That would be very much appreciated. Let's start from the status quo. So our old system. Our old system was based on AWS EMR. For the one of you which are not, who are not an AWS customers, EMR stands for Elastic MapReduce. Basically, AWS provides a managed cluster where you can find installed HDFS, so Hadoop, Spark, Flink, and some other open source software that you can use to do data analysis. And on top of that, we had to customize the instances in order for the Flink applications running on the instances to be able to connect with the rest of the Yelp ecosystem, and then reuse also some of the libraries that we wrote, like our metrics reporter or our logging infrastructure. In order to do that, we did something that is a little bit crazy. We ran a Docker container. In Docker container, we ran our Puppet monolith in order to set up all the daemons that we need to run on each host. This proved to be quite a challenge, honestly. If you ever run Docker-ized Puppet, please stop. So basically, the current system actually served us well for, I would say, around 2 years, even more. But after a while, some issues started to arise. So we stopped and we asked ourselves, is this system good enough? Is the system bad enough to change it? And the answer was just, I guess the system is just meh. Like, yeah, it's not too bad, but it's not that good either. Maybe we can do better. And honestly, like, look at this penguin. It does, I will make it bigger. It is the best meh face I've ever seen. I really like it. Anyway, so as I mentioned before, running Puppet in a Dockerized environment is kind of complicated, especially because our usual AMIs or usual infrastructure runs Ubuntu, while EMR runs a customized AWS operating system. Another problem we had was a 15 minutes time for bootstrapping a cluster, which is an eternity in 2019. And another big issue was that AWS is kind of slow with Flink updates. Took a pretty good while to just get to Flink 1.6. So yeah, not ideal. Second problem is that the whole architecture, the whole system was still pretty manual. So each cluster needed an operator, trained human operator, to manually deploy a new version or scale up resources and stuff like that. And finally, it was just different. Having a different user interaction and infrastructure from the rest of Yelp really created a high barrier to entry for both users and developers of the platform. So meet Kubernetes. Now, let's play this way. Let's say we are at blind date, so I'm going to play Kubernetes. You are the engineer. Hello, I'm Kubernetes. I'm an open source system for automating deployment, scaling, and management of containerized application. The internet says that. I like horizontal scaling. I really love it, honestly. I scale application up and down with simple command or based on CPU usage or memory, depends, you can choose. I really like self-healing systems. I can restart containers that fails, reschedule them if one of the nodes dies and stuff like that. And I also really like powerful primitives, pods, replica sets, services, jobs, and you name it. You have a lot of friends and you can use those primitives to basically model very complex applications and workflows. Now, I also have some hobbies. This joke really doesn't land, huh? All right. I also have some hobbies. I love automatic bean packing. I do it every Saturday. I place containers based on requirements and other specification in different hosts in order to drive up utilization and reduce cost. I also really enjoy service discovery and load balancing. I usually give pods their own IPs, but I can also do DNS, load balancing, port forwarding, all this kind of stuff. And finally, I really have a sweet spot for storage orchestration. I love to just automatically mount storage systems, like, I don't know, Amazon EBS, for example, on a pod, and then in case of restart, I just remount it somewhere else. I really like it. And now, honestly, if I play the part of the software engineer, I'm an infrastructure engineer after all, I think we have a lot of things in common, and that's why we got such a good friendship. Now, considering what Kubernetes offers, I'll dive into how we assemble Flink clusters on Kubernetes. This is the overview of a Flink cluster at Yelp. We'll go into every component one after one. So let's start from the job manager. I assume that everyone knows what the job manager does, but in case, we can talk after the talk. So the way we deploy the job manager is a deployment of a pod. Actually, it's a replica set of number one, but it doesn't matter. So a pod is a collocated group of containers with shared storage, network, and spec. And they're basically the scheduling unit of Kubernetes. The pods are basically what virtual instances are nowadays on AWS. Deployments instead provide a declarative updates interface for pods and replica sets. We'll see what a replica set is very soon. To automate container deployments and rollbacks. For example, you can just say, hey, deployment, deploy this version of my code using this strategy, and the deployment will do it for you. Once we have the job manager running, let's move to the task managers. For the task managers, we run a deployment of a replica set. So a replica set is just a way to tell Kubernetes to maintain a stable set of identical pods running in the cluster at any given time. And since I'd like my task managers to stay up, that's exactly what we want. That's it, really. There isn't much to it. The other piece that is probably the more weird compared to a regular self-hosted Flink cluster is this service over here. So service, pretty much an overloaded term, I know. It's what Kubernetes uses in order to overcome the lack of static IPs and static DNS. Because, having a lot of pods and containers running, it's impossible to have always the same IP associated to the same pod, because the pod can be replicated, can be scheduled somewhere else, can fail and then restarted. So what Kubernetes does is exposing an application running on the cluster, like a network service, and then he exposes these rules to the rest of the cluster thanks to a proxy. So basically these proxy, in our case we use kubeproxy, are able to route traffic towards the end of a service thanks to very clever IP tables modification, and thank to God we don't need to do because Kubernetes does it for us. And then we can implement on top of it for forwarding and round robin. Now, the last bit is the supervisor thingy, and if you don't work at Yelp, I hope you never heard of it, because it's not open source, so there we go. So at Yelp, Flink jobs are deployed by the supervisor. This is an in-house daemon that we actually built in order to introduce some automation on top of our old EMR solution, because on EMR there was no way to extend the logic for cluster deployment, while on Kubernetes there is, and spoiler alert, we'll see it in a minute. So the supervisor is in charge of job deployment, state management, monitoring, and a couple more things, and it is not necessary in a Kubernetes deployment. Actually, if you're starting from scratch, please don't do it. We needed to integrate it because it was pretty hard for us to migrate all the users that we have, all the applications that we have, without replicating something similar to our current platform. And this is actually a pattern that I would recommend if you're migrating from a very stable and maintained platform to something that is newer and maybe fancier, but still you don't want to make your user's life miserable just because they're migrating to something newer and shinier. So yeah, we run the Flink supervisor still on Kubernetes thanks to a job. So what is a job? A job is a way for Kubernetes to create pods and ensure that a specified number of them, in our case one, successfully terminate, so the exit to status 0. We need a job instead of a simple deployment because we use the supervisor to signal the shutdown to a cluster. So the supervisor will basically say, hey, Flink, please shut down these jobs, and then we'll wait. And as soon as this job terminates, so as soon as the supervisor terminates and all the set points have been taken and the job stops, then we know it's safe to remove the resources from the clusters. Now, let's say that we know how to deploy a Flink cluster now. We know all the components. We could write an Helm chart and deploy it, or doing by hand, just with the CLI or querying the API. The problem is that this doesn't scale, right? This is kind of manual, and there's not so much of improvement compared to before. So in order to do that, we built an operator. So what is an operator? This is a pretty famous jargon in the Kubernetes world, and this is the actual definition. I'm reading. Operators are software extensions to Kubernetes that make use of custom resources to manage applications and their components. The internet says this as well. So in our cluster setup, the Flink operator sits outside, and it just creates the cluster and manages it over time. Yes. So in order to better understand what an operator does, let's basically compare left and right what a human operator does and the Kubernetes operator does. So first of all, they both manage a service or a set of services. So far, so good. They have a deep knowledge of how the system works, and they know how the system is expected to behave. So they also know how to deploy it and how to react if there is any problem. Now, so far, they are exactly the same thing. The difference starts here. So a human operator, like me and you, usually use automation for repetitive tasks because they're boring, while a Kubernetes operator really doesn't mind and automates repetitive tasks. And finally, while myself, I can only manage a very limited number of instances before I make a mistake, actually even one is too much, a Kubernetes operator can manage a very high number of instances before running into any scalability issue or making mistakes, as long as you didn't introduce any bug in it. So the operators is also a way to add a lot of logic to your cluster deployment. For example, you don't need to familiarize with the whole chart, but in the operator, we implement a small state machine in order to make sure that the shutdown of our Flink clusters works perfectly every time. The way we do this is that we signal the operator with a custom annotation saying shutdown on a custom resource. So these are very weird words, and let's look into it. What is a custom resource? So a custom resource is a declarative model of an application or a workflow. In our case, it is just the deployment of a Flink cluster. And it also holds this representation of the state that the cluster is in. The operator then looks at the custom resource, looks at the state, and takes decision based on that. For example, if the actual state of the custom resource, so the cluster, is different from the expected one, then it will make some modification to it, so it will reflect the expected one. And finally, we have labels and annotations. They are just tags, really. And they're basically used for selecting components or for signal stuff to the operator. In this case, if we go back, we use the shutdown annotation to basically say to the operator, hey, it's time for you to shut down this cluster. So in the operator, you can encode really any logic that you want. For example, we encode the logic to have our Flink dashboards in production being accessible from the browsers of a user and also provide authentication because, security is important. In order to do that, we added one more component to the cluster. It's called an ingress. So in ingress, it's a way in Kubernetes to basically punch a hole in the cluster and makes something available from outside. So in this specific case, the ingress exposes some HTTP and HTTPS routes so that a user from its browser can actually access the Flink dashboard. The way this works, it's pretty interesting, actually. There is an ingress controller, which is just almost a synonym for operator, which manages the ingress resource that we created. So if we go back here, let's see if I have another slide. Yes, I do. So we create the ingress with our operator, but we don't do anything else. And then there is this open source ingress controller running on the cluster, actually setting up the cluster in a way that these ingress rules are a thing. We also use Nginx as a proxy, and it's where we do the authentication. Now, once again, this is very Yelp specific. You don't need to familiarize with the whole chart. But this is one example of the things that an operator can do for you if you have the time to encode it. Now, last part of the talk, let's talk about PaaSTA. PaaSTA is our platform as a service, as I mentioned before, and it has a fantastic logo, as you can see. I really like it. Reading their definition from our blog, is an highly available distributed system for building, deploying, and running services using containers and Apache Mesos. And Kubernetes nowadays, we are migrating, as anyone in the world, I guess. Basically, this is not too different from what Kubernetes does. PaaSTA is just an opinionated way of doing deployments and rollouts and everything that is very tailored to Yelp. It's open source if you want to check it out. The reason why it's so opinionated is that because we believe it makes the life of the developers and the users of the platform much, much easier. Let's look at that. Actually, before doing that, why are we even integrating? Because actually, if you have an operator and some custom resource, you can just run your Flink clusters and you may be happy. And that's a question we get a lot. Why didn't you just use one of the Flink operators that were open source out there? Well, first of all, there was none when we started, so that's a good reason. But the second reason is that we really wanted to integrate our platform with the rest of the Yelp ecosystem and the rest of the Yelp user experience so that we don't create an high barrier to the users. In fact, Implementing a consistent interface for every PaaSTA users really makes much easier for every user to interact with the cluster and deploy a new one, because it just looks like any REST services at Yelp. In addition, integration with PaaSTA allows us to really expose infrastructure as a service, which is kind of the dream in our line of job. So whether it's a web server, a Cassandra cluster, a Flink job, you name it, for the users, everything is a service, even if it's a piece of infrastructure. And finally, as a platform engineer, I become a user too, because we have teams dedicated to PaaSTA support, and basically we share the infrastructure and tools with the rest of the user that we can just use, like libraries and CLIs and stuff like that. Basically, I don't maintain virtual instance anymore. Now, this is basically the diagram of how our Kubernetes Flink operator interacts with PaaSTA. Once again, you don't need to familiarize with it all. Let's just look at two things. The first one is this repository. It's called Yelp configs. It's just a YAML repository, because we love YAML. Basically, every time you want to define a cluster, what you need to do is writing this kind of YAML specification and committing it. And then PaaSTA will automatically read the YAML and then create a custom resource, which is exactly what's contained in this YAML file, plus some, plus some reasonable default values. So this is why they're called actually custom resource definitions, because the users writing the developers writing the operator can actually customize them for their own needs. For example, for Flink, we have the number of task managers with their CPUs and memory, the checkpoint interval, the path, some options. It's all stuff that we decide beforehand and decide to expose to the users. It's all documented, and it's just here. No need to know anything else more than the specification. The second bit is this service repo over here with the Docker file. So, well, I assume that this works more or less the same in any company. You have some kind of Git repository or some other repository with your service code. And in order to deploy it to Kubernetes, you need to define a Docker file. So the way we do it is that my team, stream processing over here, maintains a set of base Docker files, one for each Flink versions. They also install some Yelp dependencies, and then we publish them to our Docker PaaSTA registry. The user write their service code, and then they define a simple Docker file inheriting from one of the base Flink images, and then they just add the code to Docker file and push it. Once it reaches the Docker PaaSTA registry, and it's matched with a YAML resource definition in Yelp configs, then our operator will pick it up and create the service instance, so the Flink cluster. The user interaction with the cluster, it's very, very easy, actually. If you want to check the status of your cluster, you just run PaaSTA status, and it's the same for everything deployed on PaaSTA, regardless of whether it's Flink or not. If you want to read the logs, you just do PaaSTA logs. And if you want to deploy a new version, and this is actually the killer feature, I would say, you just commit the new version and git push origin master. That's it, and you have the new version running. So that's basically the end of the talk almost. But before moving to the question, I wanted to basically show you the future that we have in mind. Also, don't you like the cow with the aliens? Isn't it super cool? Anyway, so one thing we're experimenting with, it's Python on Bing, on Flink, on Kubernetes, on PaaSTA. So we are a Python shop at Yelp. So running Flink for us is cool. It allows a lot of use cases, honestly, but we still have hundreds of stream processing jobs written in Python who are running on our custom stream processing framework, which is not great, I must say. So basically, with Apache Beam, we will be able to take these jobs and move it to Flink. And that's, for us, really one of the killer features. So at the moment, we are working on integrating our Apache Beam with Kubernetes. So here we go. Another thing we're working on is a pipeline builder. I know that some companies have it already. They even sell it, but we don't have it yet. So what we'd like to do is exposing a kind of a DSL or a configuration file, we're not sure yet, to the users, so they can basically create complex pipelines without writing any single line of code. For example, we can take Kafka streams and let's say we manipulate it with Flink SQL, then we pipe it into a custom Beam service, and then we write the results to S3. Or we can also take the results, join it with another Kafka streams, and then finally write it to Elasticsearch. This is not different from an actual pipeline that we run, and it would be fantastic if we could give the developers the possibility to just specify a very high-level view of the pipeline, and then we take care of the rest. We also have smaller improvements to the old platform. For example, we would like to try job-oriented deployments. They give us more isolation, faster starts, and just a simpler deployment strategy. Even though it comes with some challenges, because we have some application that generates jobs automatically, and that's kind of complicated. Second, we are really waiting for the reactive container mode. So please do it. So we can auto-scale our load, which is kind of a pain at the moment. And finally, we would like to move away from the supervisor as much as possible and codify all the knowledge that we have, the state management, the job select cycle, the save points, everything, into the actual operator. And maybe just have the supervisor doing our Sensu integration, because we use Sensu for monitoring. Finally, this would be my takeaway slide. But then I thought, Antonio, they sat with you for I don't know, half an hour, even more. And probably the only question they have in their mind is that, yeah, that's all cool, Antonio, but should I do it? Well, should you do it? Yes, I think you should, actually. So for mainly 3 reasons. The first one is that finally you can scale up your deployments, the number of clusters of Flink that you run, without scaling up the team maintaining those clusters, which is a fantastic feature. That's why we write software. The second thing is that operators are a great way to codify knowledge. And honestly, it's so much easier to write some code instead of passing down these kind of war stories to new hires. Also, code is the best documentation because it doesn't go out of date. When it does, it breaks. And third, it is a catalyst for users. Integrating with our platform really make our user much happier to use Flink application. Also, they don't need to know how to deploy a Flink job or a Flink cluster anymore because PaaSTA does it for them. Finally, I know that I didn't cover them in my talk, but I want to be honest. There are also reasons why you may not want to do it. The first one is that there is a Kubernetes tax to pay. If you never integrated Kubernetes in your platform, then it takes some effort. So yeah, that's a bit of a con. Second, whether you're building your operator or you're taking something off the shelf, Lyft has open source its own operator, Google as well. So you can take one of those and run it in your Kubernetes cluster if you want. So whether you're building it or fitting an existing one, it's still going to take some time and some problems and some incidents to make it right. So that's something to consider, especially because now there is always the cloud. And some platforms, as you see in Google, AWS, they are starting to provide managed platforms for your Flink and stream processing deployments as well. And I guess that's it. We're also hiring, both in London and San Francisco, if you want to work with me or my colleagues. And please stalk us on literally any social network. And questions, suggestions, tomatoes, anything? And thank you for sitting with me for the whole thing. Do we have time for questions?
I think we do. I actually didn't check. Yes, I think so.
Great.
Okay, thank you so much for your talk. Any questions? Okay.
Hi. Do you do anything with fine-grained resource allocation in Kubernetes? So you're assigning more memory and a fractional CPU to the job or something like?
No, but that would be great. Yes, it's in the roadmap, maybe in the future.
Any other questions? Maybe in the back?
No one? There we go.
Maybe in the front.
Have you had any issues with network I/O when different jobs are bad neighbors and?
That's actually a very good question. So we run our Flink clusters in a separate pool compared to the rest of the company for many reasons. One of those is security, even if we're lifting it. But one is bad neighbors. So for example, we are a bit scared that people will, so basically we use checkpoint and save pointing on disk through RocksDB, and then we save it externalized to S3. And we're a bit scared that someone will gonna misuse the disk and basically create a problem for us. Kubernetes, if you run some specific file system, as a way to enforce limits on the size, but still, the IOPS are going to be a problem. So yes, that's a concern, but I guess it comes with any, kind of savings that you get with these cloud platforms, right? So yes, I guess it's a trade-off.
More questions? Okay, let's just wrap it up. Thank you so much for the great talk.
Thank you.